two terminals here. With the question, they want us to find Thevenin equivalent circuit. Okay, so we know the Thevenin equivalent circuits. We have your VTH in series, and this time is RTH, and that's basically what you're trying to do. And obviously, your RL will go here. Yeah, that's your load resistor, okay? So we need to find RTH, just like before, and we need to find VTH. Remember, VTH is called V open circuit. So you remember that, right? So cool, so I start with the RTH, and well, the accents for the maximum power transfer. For 2 marks, that chalk and cheese, because just plug in values into the equation, right? So cool. So let's do the RTH. So same steps as before, so we're a little faster in this one. So we know we're looking in from these two terminals here, A and B. So we need to turn off all the independent sources. So this branch here, it gone. Why? Because this open circuited. Anytime you open circuited, it's basically disappearing, right? So and this short circuited. So the whole circuit does not end up being, so you have 5 ohm here. Then you have a resistor on top. Resistor going through the short circuits. And a resistor at the bottom. So this is 8, 4, 8, and 5. And probably for this one, if you ain't seeing it, same thing. So how fast I'm gonna do that? So you have A, so B, A, and this one you call it C, and this one you call it D. So this one have 2 extra nodes in it, which is okay, it will make a big difference. So we starting with A. So that's one, but I write the nodes in a as a sequence, right? So A, you then write C, then D, and then B is the output. And that replaces resistors in between the nodes that it's in. So this 8 ohm here between A and C, so we'll right here. Particle beds, this 4 ohm between C and D, so we'll right here. 8, put a tick by it to know. This 8 ohm between D and B, so right here. And then put a tick by it. And this 5 ohm between A and B, so go at the bottom. A to D, 5. Yeah. And we just keep going. So obviously now you're seeing what's stuff in series, so you connect the lines. Nice, so this should be way easier to see. So we're seeing the 8, the 4, and the 8 basically in series with each other, and that is in parallel with the 5. So we just redraw the circuits. So 20 and parallel with 5. And sadly, these two are not the same value, so we have to do the full product over some, right? So RT will be the product of them divided by the sum of them. Product over sum. So this will be 100 divided by 25, which is 4. Yeah, and that is the RT. So remember, we're doing Thevenin, so the RT in this case will be our RTH. So that is the first piece done and dusted, right? Next thing we do, we're going to find VTH. So remember, to get VTH, yep, put back all the independent sources, make sure it's there. So once those back in the circuits, obviously this RL go on already, and it's already open circuited, right? So we're basically looking for the voltage between these 2 points here. Okay, so luckily for us, well, sadly for us, this 8 ohm preventing me from just slapping one big ground at the bottom here, right? So because this node here wouldn't give me much value if I put it as 0. So you're looking to see which node will give you the most value if you put it as 0 as the reference. This one really gonna do much, right? But this one will do a lot, because if you make this one 0, you actually know what this node is. So you're kind of killing 2 birds with 1 stone. If you just make this 0, you will have an unknown node here, an unknown node. So you basically end up with more unknown nodes. So you try to pick the node that will give you the most bang for your buck in terms of the reference. So this one will be the best, right? So let us be a reference. And if that is a reference, this node after the battery will be a G, B, N node. So if you look at the polarity going from 0 minus to plus, so this will have to be 12 here, right? And we have no other nodes that we know the voltage for. So let's analyze it a little bit. So we're looking for A and B, the voltage between these two will be Thevenin. So next thing we do, we label the other nodes. So we draw any nodes. So we have a node on top here. We label this one VC. And we have a node at the bottom right here. It will be VA already. And we have this one at the bottom here, which is VB. Right? Because that B already here, so you put VB. Let's have A already here, so you put VA, so you have VC, right? So when we do any question now, looking at the voltage, since this is not 0, sadly, like the one before, the V will be the difference between VA and VB. So for example, if we had get VA to be 10 and VB was 2, the V will just be 10 minus 2, which is 8, right? So same concept. So we use a nodal analysis, so we could rush down our nodal analysis. So the first one we do, obviously, we assume a current direction for all nodes. So I just always do out, so I just keep it. So you assume currents going out for all the nodes. Right, this piece here have no current, but this open circuit, right? So this branch not really here, right? So we have these two. So how much unknown nodes we have? We have basically VA, we have VB, and we have VC at the bottom here. So we basically have 3 nodes, and we have 3 equations. So we need 3 equations to actually get the value. So the first one we'll do VA, since it's just the first one that we have. So for VA, so remember the little trick. Once you assume the current directions is where it's coming from, minus the node they're going to, divided by the resistor in between it. That's literally the equation for them, right? So in this case, we have one endpoint here. So you're coming from VA. So we're coming from minus the node they're going to, which is VC, divided by the resistor in between it. So like one endpoint done. And we have this endpoint here. Same thing, you're coming from VA minus you're going to VB, and you're divided by the resistor in between it, which in this case is the 5. We don't need to do this one, it's basically 0 because it have no current flowing in this branch, right? So you make that equal to 0. And remember, we're trying to simplify. So you just multiply the equation by 40. So you multiply both equations by the 40, so you get 5 VA minus 5 VC. And then 5 into 40 is 8, so you get plus 8 VA minus 8 VB. And you make it equal to 0. And just like we did before, you simplify. So 5 and 8 for the VA, then you have minus 8 VB. So let's keep going. So you have 8, 5 and 8 is 8, 9, 13. Minus 5 VC, and you have minus 8 VB, and equal to 0. Yeah, so that the first, we call this the first equation, right? So you just write that down at the bottom and then use the rest of the space. So we have 13 VA minus 8 VB minus 5 VC, and that is equal to 0. And that's the first equation. So we have probably like, so now we need to do it for our VB. So we just go in sequence. So for VB, same thing, assume the currents going out, and the same concept. So we have this part here. So where coming from is VB minus we're going to divided by the resistor. So for this one, it will be, so for VB, so you're coming from VB and you're going to 0, and you're divided by the resistor in between it. So that is this end piece here. We don't need to do this end piece, nothing going on here. And we have this end piece here, so you have VB. We're coming from minus, we're going to divided by resistance. And then you make it. And you just simplify that's like normal. So in this case, we could multiply both of them by 40. So you basically end up with the 5 to be at the end, you end up with 13 VB minus 8 VA, and that will be equal to 0. And that will basically be equation 2. And then you go again. So we have one more node, which is the VC node. And just like before, you have this branch here, but we have a current source here. So the current that going through here will basically be the current that the node will see in the correct polarity, right? So in this case, for VC, the first one will be minus 2. Why is it minus 2? Because the current that we assume is opposite to the current that's here. So that's going so, and we wobble so. So that's invert the value. So the current for this piece here will be minus 2. Then we have this one here, same thing, there's a normal branch. So we're coming from minus, we're going to divided by resistance between it. So plus coming from VC minus 12 divided by 4. We have one more endpoint on top, which is here. So you're coming from VC minus we're going to, which is VA, and divided by the 8. Yeah, and then make it equal to 0. Don't forget to make it equal to 0. And just like before, we're trying to simplify it. So the common denominator we could use here is 8. So you multiply everything throughout by 8. And it'll basically, at the end up it's minus VA plus 3VC is equal to 40. And that'll be the third equation. Yeah, so now you have 3 unknowns and 3 equations, right? So this is where we use your calculator or solve it simultaneously. By using a calculator to solve it simultaneously, okay? So the 3 equations I will have, if I put it in the form, so I have thirteen VA minus 8 VB minus 5 VC equal to 0 as equation 1. And we have this one here, so it'll be minus 8 VA, then plus 13 VB, and then plus 0 VC, and that is equal to 0. Second equation. And the one at the bottom, which is basically minus VA plus 0 VB plus 3 VC is equal to 40. And that will be the third equation. So you're basically solving these simultaneously. Right? So once you solve it simultaneously based on the values that we want to get, you'll end up with VA being 10.4 volts. Let's write it better. So you calculate all your calculations will give you 10.4, and you'll end up with VB being 6.4 volts. And that's right before, remember, we have here and we have here, and we need the difference between it, right? You always look at the voltage difference. So finally, VTH will basically just be VA minus VB, which is 10.4 minus 6.4, and I'll give you 4 volts. So now, as a caveat, I think somebody had asked me if they wanted the Norton equivalent circuit. I could go from the Thevenin straight into the Norton because I know the equation VTH is equal to I Norton by RTH, and I already have RTH, and you just get V Thevenin. So if I wanted iron to go into the Norton equivalent circuit, I would just need to divide 4 by the value you get for RTH, which was, well, 4, and you end up with 1 for the I note. And you just draw your Norton equivalent circuit. Yeah? So that is basically the easiest way you could jump. Same marks, you just use a different method. Reason being because you have an equation that has linked both equations or both equivalent circuits together. Right? But this question asks for Thevenin, so I'm just draw it. So we have 4 in series with the RTH, which is 4 ohms. And that is it. And access for maximum power transfer. So remember, maximum power transfer, so you put back your R load. Your maximum power transfer will occur when your load resistor is equal to RTH. So, and this is Thevenin, so we know the equation you use will be the V Thevenin squared by 4 RTH. So it'll be 4 squared divided by 4 by RT plus 4, and you'll basically end up with 1 watt. And that basically be that question. So same concept, just a different application. So make sure you all know how to solve the equation simultaneously, right? Because that is the part that will take up the most time. If you calculate that, because if you're not Casio, because Casios could solve I think 4 variables, 2 variables and 3. If you don't know how to do that, make sure you know how to solve equations simultaneously. Right? Make sure you know how to do that. Alright, so at the end of this, the other question. Any questions on this one?